Dear viewers, today we shall talk about some more applications of the Laplace transformation. In my last lecture we had discussed some applications of Laplace transformation, like application of Laplace transformation to the problems in dynamics, then the application of Laplace transformation to a simple electrical circuit. We shall today discuss the application of Laplace transformation to bending of beams, and then the application of Laplace transformation to problems in mechanics. We shall also discuss the application of Laplace transformation to boundary value problems, like how to find the solution of a heat conduction equation and how to find the application of a wave equation by using Laplace transformation. So, let us begin with a problem on an electrical circuit. Let us find the current IT in the LC circuit. Here we are considering only LC circuit. R is not there, that is resistance is not there. We are assuming L to be of 1 Henry, C to be of 1 farad, and with initial current 0 and initial charge on the capacitor also 0, and we are given that Vt is equal to T when 0 is less than T less than 1 and 0 otherwise. Vt means the electromotive source of voltage Vt. Now, in this case, in the case of the given problem, the governing equation will be L di by dt plus q by c equal to E, but I we know is dq by dt. So, we get L d square q by dt square plus q by c equal to E. E is the E here will be replaced by B, that is Bt. So, and we are given that L is equal to 1 and C also equal to 1. So, L is equal to 1 and C equal to 1, let us put, and we put E equal to Vt, but Vt is equal to T when 0 less than T less than 1 and 0 otherwise. So, we can replace Vt, we can write Vt in terms of unit step functions as T times u naught T minus u1 T. So, if we do that, we will have the differential equation like this: d square q by dt square plus q equal to T times u naught T minus u1 T. Now, let us apply Laplace transform to this equation. L of d square q by dt square we know will be given by s square q r minus s q 0 minus q dash 0, then L of q is q bar, and then we have Laplace transform of t into u naught minus Laplace transform of t into u1 t. Now, let us substitute q 0 equal to 0 and then I 0, that is q dash 0 equal to 0. We will have s square q bar plus q bar equal to, now Laplace transform of t into u naught t is equal to e to the power minus 0 s into Laplace transform of t, because we know that Laplace transform of f t into u a t is e to the power minus s into Laplace transform of f of t plus a. Here a is equal to 0. So, we get e to power minus 0 s into Laplace transform of t plus 0, that is t, and then Laplace transform of t into u1 t similarly will be e to the power minus s into Laplace transform of t plus 1, because here a is equal to 1. And now, simplifying this, we have then q bar equal to 1 over s square plus 1. Laplace transform of t we know is 1 by s square minus e to the power minus s multiplied to Laplace transform of t plus Laplace transform of 1. Laplace transform of t is 1 by s square and Laplace transform of 1 is 1 by s. So, we get q bar as 1 by s square plus 1 multiplied to 1 by s square minus e to the power minus s by s square minus e to the power minus s by s. Now, let us take the inverse Laplace transform of this equation. Left hand side will give us q, and the right hand side using linearity we will have q equal to L inverse of 1 over s square into s square plus 1 minus inverse transform of e to the power minus s over s square into s square plus 1 minus inverse transform of e to the power minus s over s into s square plus 1. Now, we know that the inverse transform of 1 over s square plus 1 is sin t. So, inverse transform of 1 over s into s square plus 1 we can write as integral over 0 to t sin t dt, because we know that Laplace transform of integral over 0 to t f t dt is f s by s, where f s is the Laplace transform of f t. So, making use of that theorem, we have inverse transform of 1 over s into s square plus 1 equal to integral 0 to t sin t dt, and which is equal to 1 minus cos t. Now, let us find the inverse transform of 1 over s square into s square plus 1. So, again making use of that theorem, where we have said that Laplace transform of integral 0 to t f tau d tau is equal to f s over s. Making use of that theorem, again we now have integral of inverse Laplace transform of 1 over s square into s square plus 1 as integral 0 to t, and then inverse Laplace transform of 1 over s into s square plus 1, which we have found as 1 minus cos t. So, this will, when we integrate this and put the limits, we get the inverse Laplace transform as t minus sin t. And then let us apply second shifting theorem. Inverse Laplace transform of e to the power minus s over s into s square plus 1 will be equal to then 1 minus cos t minus 1 into u t minus 1, because we know that inverse Laplace transform of e to the power minus s into f s is equal to f t minus a into u t minus a. So, here a is equal to 1 and f s is 1 over s into s square plus 1, whose inverse Laplace transform we have seen comes out to be 1 minus cos t. So, by second shifting theorem we have inverse Laplace transform like this. And then similarly, the inverse Laplace transform of e to the power minus s over s square into s square plus 1 may be written. It will be equal to t minus 1 minus sin t minus 1 into u t minus 1. And therefore, we will have q equal to t minus sin t minus t minus 1 minus sin t minus 1 into u t minus 1 minus 1 minus cos t minus 1 into u t minus 1. Now, let us discuss the application of Laplace transform to a problem in mechanics. Two masses m and small m free to move in a straight line are connected by a spring of stiffness lambda. At t equal to 0, when they are both at rest and the spring unstrand, a blow of impulse p is given to m in the direction towards small m. We have to find the motion of the mass capital M and the small m. So, let us say that let us say this is our spring, a is its natural length, and x and y are the displacements of the mass capital M and the small m from their original positions at time t equal to 0, that is from the equilibrium position. So, at time t equal to 0, the mass m is at distance x from the origin, and this mass m is at the distance y plus a, where a is the natural length of the spring and y is the displacement of the mass m from its original position. Now, then by the Hooke's law, it follows that the compression in the spring will be given by t equal to lambda times x minus y, because lambda is the spring stiffness of the spring and x minus y gives us the compression. So, this will be the compression in the spring. The equations of motion of m and small m will then be given by mx double dot will be equal to p delta t minus t, because p, the blow of impulse p is given to the bigger mass m, to the capital to the mass capital M, and so the equation of motion for the mass m, capital M, will be mx double dot equal to p delta t minus t, while for the smaller mass m it will be m by double dot equal to t. And now, let us put the value of t equal to lambda times x minus y in these two equations. We will have mx double dot plus lambda times x minus y equal to p delta t, and m by double dot equal to lambda times x minus y, which we can write as m by double dot plus lambda times y minus x equal to 0. The initial conditions are at t equal to 0, x is 0, y is 0 and both the masses were at rest. So, x dash and y dash are also 0, x dash is the derivative of x, that is dx by dt, and y dash is dy by dt. Now, let us take the Laplace transform of this equation. So, Laplace transform of this will be m times s square x var minus s x 0 minus x dash 0. Making use of the initial conditions x 0 equal to 0, x dash 0 equal to 0, we will have the Laplace after taking Laplace transform of this equation, we shall have m s square plus lambda times x var minus lambda times y var equal to p times lambda p times L of delta t, Laplace transform of delta t. Now, we know that Laplace transform of delta t minus a is equal to e to the power minus s. So, taking a equal to 0, we get the Laplace transform of delta t as e to the power 0s, that is 1. So, we have the right hand side, Laplace transform of the right hand side as p, and when we take the Laplace transform here, we get m times s square y var minus s by 0 minus y dash 0. Again by 0 is equal to 0 and by dash 0 equal to 0 implies that the Laplace, after taking Laplace transform of this equation, one will have m s square plus lambda into y var minus lambda x var equal to 0, where x var denotes the Laplace transform of x and y var denotes the Laplace transform of y. Now, we multiply equation by m s square plus lambda, the second by lambda and then add this. By doing this, we will be eliminating one variable, that is y var, and we shall have this equation in x var. So, m s square plus lambda into m s square plus lambda minus lambda square into x var equal to m s square plus lambda into p. We had a system of simultaneous equations in x var and y var. By eliminating one variable y var, we got this equation in the variable x var, which after simplification gives us x var equal to m s square plus lambda over s square times s square plus lambda into m to the power minus 1 plus capital M to the power minus 1 into p by m m, which we call as equation number 2. And we can write this further as x var equal to p over m plus m into 1 over s square plus m into m to the power minus 1 over s square plus lambda times m to the power minus 1 plus capital M to the power minus 1. That is, we break it into its partial fractions, and then we take the inverse Laplace transform of this equation. So, inverse Laplace transform x bar gives x, p over m plus m is a constant, inverse Laplace transform 1 over s square is t, and then m into m inverse is a constant. Let us call lambda into m to the power minus 1 plus capital M to the power minus 1 as p square. So, that we have inverse Laplace transform of 1 over s square plus p square, which we know is sin p t over p. So, when we take the inverse Laplace transform of this equation, we get this, where we have assumed that p square is equal to m to the power minus 1 plus capital M to the power minus 1. Now, from equations 1 and 2, we then can also find y var equal to lambda over s square into s square plus lambda times m to the power minus 1 plus capital M to the power minus 1 into p over m into capital M. After breaking it into partial fractions, we will have p over m into capital M into m to the power minus 1 plus capital M to the power minus 1 into 1 over s square minus 1 over s square plus lambda times m to the power minus 1 plus capital M to the power minus 1. And when we take the inverse Laplace transform of this equation, we get y equal to p over m plus m, inverse Laplace transform of 1 over s square is t, minus again here we take p square equal to lambda times m to the power minus 1 plus capital M to the power minus 1. So, then inverse Laplace transform of this is sin p t over p. Now, let us discuss the case of an elastic spring whose one end is fixed and from the other end is hung a mass m. So, such a problem is governed by this differential equation, m d square y over dt square plus k y equal to f naught sin p t, where k is the spring constant and f naught sin p t is the driving force. Because of this force, at y is the displacement in the mass m at time t. And by Hooke's law we know that the spring force will be k y, because k is the spring constant and y is the displacement in the spring from the equilibrium position. So, k y will be the spring force. So, resultant force will be f naught sin p t will be acting downwards, while k y force will be acting upwards. So, resultant force will be f naught sin p t minus k y, and that will be equal to m into d square y by dt square. Now, we are assuming that initially the mass is at rest in the equilibrium position. So, we will have y 0 equal to 0 and y dash 0 equal to 0. And when we take the Laplace transform of the governing equation of motion of the mass m, we have s square by bar s plus omega square into y bar s equal to k into p over s square plus p square, where we have assumed that omega is equal to square root k by m and capital K denotes f naught over small m. So, when we solve this equation for y bar, we will have y bar s equal to k into p over s square plus omega square into s square plus p square. Now, we will break it into partial fractions and then take the inverse Laplace transform in order to find the displacement of the mass m at time t. So, there are two cases. One is if omega square is not equal to p square, then when we take the inverse Laplace transform after breaking into partial fractions, we get y t equal to k p over p square minus omega square into sin omega t over omega minus sin p t over p, and this case corresponds to no resonance. If omega square is equal to p square, then the inverse Laplace transform will give us y t equal to k over 2 omega square into sin omega t minus omega t into cos omega t. This is the case of resonance. Now, let us study another problem of mechanics, where we have two masses connected to three springs. We have, and all the three springs have the same spring constant k, the stiffness. So, here the governing equations of motion for the mass m, m1 and the mass m2 are these two equations. For the mass m1 we have y1 double dash minus k y1 plus k times y2 minus y1, where we have made use of the given value of m1, that is m1 equal to 1, and for the mass m2, which is again given to be equal to 1, we have the equation of motion as y2 double dash minus k times y2 minus y1 minus k y2. Now, when the because of the mass m1, let us say at time t, the displacement in the spring, this first spring is y1. So, so then the k y1 force, that is the spring force, will act upwards, and this mass m1 will compress this lower spring. Okay. So, then there is a displacement y2 in this mass at time t. So, the net resultant displacement will be in the mass m2 will be y2 minus y1. So, for this lower spring, k times y2 minus y1 will act upwards for the mass m1, while for the mass m2 k times y2 minus y1 will act upwards, and also k y2 will act upwards. So, we have for the mass m1 the resultant force will be k times y2 minus y1 minus k y1, while for the mass m2 it will be k times y2 minus y1 minus k y2 plus k y2, which is acting upwards. So, we have put negative sign here, where k is the spring modulus of each of the springs, y1 y2 are the displacements of the masses, from their positions of static equilibrium, we are assuming that the masses of the springs and the damping is negligible. So, the initial conditions here are at t equal to 0, by 1 equal to 1, and at t equal to 0, by 2 is equal to 1. At t equal to 0, dy 1 by dt is equal to root 3 k, and dy 2 by dt is equal to minus root 3 k. Let us take now the Laplace transform of both the equations of motion for the mass m1 and m2. Then we shall have, for the mass m1 we shall have s square by 1 bar minus s minus root 3 k minus k by 1 bar plus k times y 2 bar minus y 1 bar. In the left hand side there we had y 1 double dot by d square by 1 over dt square. So, when we take the Laplace transform of that, we have s square by 1 bar minus s by 1 0, by 1 0 is equal to 1, then minus by 1 dash 0, and by 1 dash 0 is equal to root 3 k. So, we have the left hand side after taking the Laplace transform like this. The right hand side we had k minus k by 1 plus k times by 2 minus by 1. So, when we take Laplace transform of the right hand side, we get minus k by 1 bar plus k times by 2 bar minus by 1 bar. And when we take the Laplace transform of the second equation of motion, that is the motion of the mass m2, we have s square by 2 bar minus s by 2 0, by 2 0 is 1 plus minus by 2 dash 0, but the by 2 dash 0 is negative root 3 k. So, we have plus root 3 k here equal to minus k times Laplace transform of by 2 minus by 1, which gives us by 2 bar minus by 1 bar minus Laplace transform of k times by 2, that is minus k by 2 r. And when we eliminate the variable by 2 r here, we get by 1 bar equal to s plus root 3 k into s square plus 2 k plus k times s minus root 3 k over s plus 2 k whole square minus k square, and by 2 r comes out to be s minus root 3 into k plus into s square plus 2 k plus k times s plus root 3 k over s square plus 2 k whole square minus k square. After breaking into partial fractions, we get by 1 bar equal to s over s square plus k plus root 3 k over s square plus 3 k, and by 2 bar becomes s over s square plus k minus root 3 k over s square plus 3 k. Now, let us take inverse Laplace transform of these two equations. They will give us the displacements of the masses m1 and m2 at a time t. So, by 1 t comes out to be cos root k into t plus sin root 3 k into t, and by 2 comes out to be cos root k into t minus sin root 3 k into t. Now, let us study application of Laplace transformation to deflection of beams. So, let us say we are given a beam which is kept along the x axis, and it is of length L. Its one end is at x equal to 0, the other end is at x equal to L, and let us suppose that the beam suffers a transverse deflection by x, which is produced by applying a vertical load to the beam, say w x per unit length. Then the deflection is given by this differential equation d4 by over dx4 equal to w x over E I for x varying from 0 to L, 0 less than x less than L. Here E is the Young's modulus of elasticity for the beam, and I is the moment of inertia of a cross section of the beam about the x axis. The boundary conditions are, if the beam is hinged or has simply supported ends, then at those ends by and by double dash are zeros. If the beam is clamped at both the ends or it has fixed ends, then at those ends by and by dash are zeros. Now, if the beam has a free end, then at that end by double dash and by triple dash are zeros. Let us now study an example of a beam of length L which is clamped horizontally at both its ends and loaded at x equal to L by 4 by a bait capital W. We have to find the deflection y at any point and also the maximum deflection in the beam. So, as we have seen, the equation for the deflection of the beam is given by E I d 4 by over d x 4 and the weight, this is a point load here W. So, we write the right hand side as W times delta x minus L by 4, it is applied at the point L by 4. So, we write W into delta x minus L by 4. The boundary conditions are, because the ends of the beam are clamped. So, the boundary conditions are y and by dy by dx both are 0 at the ends x equal to 0 and x equal to L. When we take the Laplace transform of this equation for the deflection of the beam, we will have S 4 y bar equal to W over E I into e to the power minus L s by 4, because Laplace transform of delta x minus L by 4 gives you e to the power minus L by 4 into s, and then plus s by 2 plus by 3, where we have made use of y naught and y 1 equal to 0. Y 1 denotes dy by dx at x equal to 0, y naught is y at x equal to 0, y 2 is y double dash at x equal to 0, and y 3 is y triple dash at x equal to 0. Now, let us take inverse Laplace transform of this equation. So, we will divide this equation by s to the power 4 and then take the inverse Laplace transform. Y bar is equal to W over E I e to the power minus L s by 4 over s 4. Then the second term will become by 2 over s cube, third term will become by 3 over s to the power 4. So, inverse Laplace transform of y bar is by, then W over E I is a constant. So, we will write it like that, and then inverse Laplace transform of e power minus by 4 over s to the power 4. Now, we know that inverse Laplace transform of 1 over s to the power 4 is t to the power 3 over 3 factorial, that is 6. So, t cube over 6 is the inverse Laplace transform of 1 by s to the power 4, but here we will have to make use of the second shifting theorem, because we have to find the inverse Laplace transform of e to the power minus L s by 4 over s to the power 4. So, we will get a here is L by 4. So, we will get the inverse Laplace transform as x minus L by 4 raised to the power 3 over 6 into u times into u of x minus L by 4, unit step function of x minus L by 4. Then we will have by 2 over s to the power 3, inverse Laplace transform of that will be x square over 2 factorial, that is x square over 2, and here we will have to find the inverse Laplace transform of 1 over s to the power 4, which is s cube by 6. Now, let us in order to find this is the deflection at any time t and at a distance x, where we have to still find the values of the unknown constants by 2 and by 3. So, for that we will have to make use of the boundary conditions at the end x equal to L. We have so far made use of the boundary conditions at the end x equal to 0 only. So, now let us but we will have to somehow get rid of this unit step function in order to find the values of by 2 and by 3. So, what we do is let us see what happens when we take x equal to L by 4, because the end x equal to L satisfies x greater than L by 4. So, with if you take x to be greater than L by 4, you will be able to get rid of u of x minus L by 4, and then you can take the derivative of y with respect to x. So, for x greater than L by 4, we have y equal to 1 by 6 into W by E I into x minus L by 4 raised to the power 3, because when x is greater than L by 4, unit step function gives us value 1, and then 1 by 2 into by 2 x square, 1 by 6 into by 3 into x cube. Now, let us take the derivative of this. So, dy by dx of this equation will give us 1 by 6 into W over E I into 3 times x minus L by 4 whole square. So, we will after simplification we get the first term like this, and then 1 by 2 into by 2 into 2 x. So, second term after simplification gives by 2 x, third term after simplification will give us 1 by 2 into by 3 into x square. Now, let us put the boundary conditions at the other end, that is at x equal to L. The boundary conditions are by and by dash are zeros at x equal to L. Then we will get from the equations for by and by dash, we will have these two equations where we have put x equal to L. So, we get these two equations, and these two are linear equations in by 2 and by 3. One can solve them. They will give us the values of by 2 as 9 by 64 into W by E I into L, by 3 as minus 27 by 32 into W over E I. Using these values in the equation for y, we will have the deflection at any time t and at a distance x given by this equation. This gives us deflection at any point of the beam. Now, in order to find the maximum deflection of the beam, at the point of maximum deflection by dash must be 0, and now let us note that for x less than L by 4, here we have for x less than L by 4 in the expression for y dash, from y dash we shall have x is less than L by 4, the expression for y in the expression for y u x minus L by 4 will be equal to 0. So, for x less than L by 4 we will differentiate that equation and get y dash as by 2 x plus 1 by 2 into by 3 into x square, where after putting the values of by 2 and by 3 we get y dash as 9 by 64 into W by E I into x into L minus 3 x. And from here we can see that when x is less than L by 4, L minus 3 x will never be equal to 0. So, L by dash is never 0 for less than x less than L by 4, and therefore, maximum deflection cannot occur in this interval. Now, let us check for 1 by L by 4 less than x less than L. Here by dash will be given by 1 by 2 into W over E I x minus L by 4 whole square plus by 2 x plus 1 by 2 by 3 x square, because u x minus L by 4 will be equal to 1 for this interval. And after we put it equal to 0, we get and put the values of by 2, and after putting the values of by 2 and by 3 and equating by dash to 0, we get this equation. From this equation, after simplification, one will have 5 x square minus 7 L x plus 2 L square equal to 0, which can be factorized into two factors like 5 x minus 2 L into x minus L, and since x is not equal to L, it is less than L, this gives you the value of x as 2 L by 5. So, the maximum deflection of the beam occurs at x equal to 2 L by 5, and the value the deflection then, that is the maximum deflection y at x equal to 2 L by 5 is then given by W into this 1 by 6 2 L by 5 minus L by 4 whole to the power 3 plus 9 by 128 into L 2 L by 5 whole square minus 9 by 64 2 L by 5 whole cube into 1 over E I R E I to the power minus 1. After simplification, the value of this expression comes out to be 63 W L cube over 8000 into E I. Now, let us study one more example on deflection of the beam. A beam of stiffness E I is simply supported at its ends x equal to 0 or x and x equal to L. It carries a uniform load W per unit length from x equal to L by 4 to x equal to 3 L by 4. Find the deflection y at any point. So, we know that the deflection equation for the deflection of the beam is E I d 4 by over d x 4 equal to W x, where W x is the load per unit length. In this case, we are given that the beam carries uniform load W per unit length from x equal to L by 4 to 3 L by 4. So, W x, the right hand side of this equation will be equal to W times u x minus L by 4 minus u x minus 3 L by 4, and therefore, and the boundary conditions, because the beam is simply supported at both its ends. So, y equal to 0 and y double dash equal to 0 at x equal to 0 and x equal to L. after taking the Laplace transform of the deflection of the beam, where we have seen that the right hand side is w times u x minus L by 4 minus u x minus 3 L by 4. So, we have and making use of these boundary conditions at x equal to 0, we get the Laplace transform of the deflection of beam as S4 by bar equal to w over E I into e to the power minus L s by 4 minus e to the power minus 3 L s by 4 over s plus s square by 1 plus by 3, since by naught and by 2 are zeros at x equal to 0. And therefore, after simplification by bar will be equal to w over E I e to the power minus L s by 4 over s to the power 5 e to the power minus 3 L s by 4 over s to the power 5 by 1 over s square plus by 3 over s to the power 4. Now, let us take inverse Laplace transform of this. When we take inverse Laplace transform of this equation, we get y equal to 1 by 24 w over E I x minus L by 4 raised to the power 4 into u x minus L by 4 minus x minus 3 L by 4 raised to the power 4 into u x minus 3 L by 4 plus by 1 x plus 1 by 6 by 3 x cube, where we have made use of the second shifting theorem. Now, for x greater than 3 L by 4, we have y equal to 1 by 24 into w over E I, because u x minus 3 L by 4 will be equal to 1, while this will be equal to 0. No, sorry, this will be equal to 1, also this will also be equal to 1. So, we will have x minus L by 4 raised to the power 4 minus x minus 3 L by 4 raised to the power 4 plus by 1 x plus 1 by 6 by 3 x cube. We are going to find the values of y 1 and y 3. So, for that we will make use of the boundary conditions at the end x equal to L, and that is why we have taken x to be greater than 3 L by 4. With this we can replace the unit step functions by their values, that is 1. And now we can take the second derivative of this y double dash gives us 1 over 2 times w over E I x minus L by 4 to the power raised to the power 2 minus x minus 3 L by 4 raised 3 L by 4 raised to the power 2 plus by 3 x. Putting the boundary conditions at the end x equal to L, that is y equal to 0 and y double dash equal to 0, we get these two equations, which are again linear in y 1 and y 3. So, we can solve them for the values of y 1 and y 3. Y 3 comes out to be minus w L by 4 E I, while y 1 comes out to be 11 by 384 into w L cube by E I. Putting these values in the expression for y, we get the deflection at any point x of the beam as this: 1 by 24 w over E I x minus L by 4 raised to the power 4 u into u x minus L by 4 minus x minus 3 L by 4 raised to the power 4 into u x minus 3 L by 4 plus by 1 x plus 1 by 6 by 3 x cube. Now, we are going to study the inversion formula for the Laplace transform. This we shall make use of when we study the application of Laplace transform to the boundary value problems. So, let us say f s denotes the Laplace transform of the function f x, then f s will be equal to integral 0 to infinity f t e to the power minus s t dt. Now, let us multiply both sides of this equation by e to the power x s and integrate between the limits a minus I b and a plus I b. We will have integral over a minus I b to a plus I b into f s f s e to the power x s d s equal to a minus I b to a plus I b e to the power x s integral 0 to infinity f t e to the power minus s t dt ds. And when you put in the right hand side s equal to a minus I b, then ds becomes minus I d p. The limits of integration for s change from a minus I b to a plus I b to b and minus b, and we get this expression on the right hand side. Or we will have integral over a minus I b to a plus I b f s e to the power x s d s as I e to the power I a x minus integral over minus b to b e to the power minus I p x integral over 0 to infinity e to the power minus a t into f t e to the power I p t dt dp. Now, let us define a function g x as e to the power minus a x into f x, where x is greater than or equal to 0 and 0 when x is less than 0. Then let us use the formula for the Fourier integral of f. Let us recall that the formula for the Fourier integral of f at each point of continuity is f x equal to 1 over 2 pi integral over minus infinity to infinity e to the power minus I lambda x integral over minus infinity to infinity f t e to the power I lambda t dt d lambda. So, let us apply this formula for the function g x. So, then g x will be equal to integral g x will be equal to e to the power minus x into f x equal to 1 over 2 pi integral over minus infinity to infinity e to the power minus I p x 0 to infinity and then e to the power minus a t into f t. Here the limits of integration from minus infinity to infinity are reduced to 0 to infinity, because g x is defined as 0 from minus infinity to 0. So, e to the power minus a t into f t into e to the power I p t dt dp, taking the limit of a minus I b to a plus I b f s e to the power x s d s, that is this. So, that is as b tends to infinity, and using the equation 3 we get integral over a minus I infinity to a plus I infinity f s e to the power x s d s as I e to the power I a x into 2 pi e to the power minus a x into f x, or we get f x equal to 1 over 2 pi I integral over a minus I infinity to a plus I infinity f s e to the power x s d s. This is the inversion formula for the Laplace transform. Here the integral is being taken over the line a b, which is parallel to the bi axis and is to the right of all the singularities in the s plane. All the singularities of the function f s into e to the power x s lie to the left of the line a b and are enclosed by this contour a b d, this contour, which consists of a b and the semicircle gamma. So, let us assume that there is a contour C which consists of a b, the line segment a b and a semicircle gamma as shown in this figure. Then the integral 4, this integral 4 along a b is equal to integral over a b d a minus integral over b d a, that is integral over a b d a. From that we subtract the integral over b d a in order to get the integral over a b. We show that the integral over b d a, that is the curved part, that is the over semicircle, tends to 0 as b goes to infinity. The semicircle is of radius b and has center at a. Let us show that if there exists positive constants capital K and small k such that mod of f s is less than k times b to the power minus small k for every point on gamma, which is described by s equal to a plus b e I theta pi by 2 less than or equal to theta less than or equal to 3 pi by 2, then limit of 1 over 2 pi I integral over gamma f s e to the power x s goes to 0 as b goes to infinity. Now, a point on gamma, for a point on gamma we can write s equal to a plus b e I theta or a plus b cos theta plus I b sin theta, because the gamma has center at the point A and its radius is b, and theta here varies from pi by 2 to 3 pi by 2. Then the modulus of 1 over 2 pi I integral over gamma f s e to the power x s d s is equal to modulus of 1 over 2 pi I integral over pi by 2 to 3 pi by 2 e to the power x s, that is a plus b cos theta plus I b sin theta into f s, and then d s will give you I into d s will give you I into b into e to the power I theta d theta. So, now this is further less than or equal to, this is less than or equal to e to the power a x into b, this b we can write here, and then mod of I is 1. So, 2 pi integral over pi by 2 to 3 pi by 2 integral then e to the power b x sin theta we have, and mod of e to the power I b x sin theta is equal to 1, and then we have mod of f s into d theta, and this is further less than k b to the power minus k plus 1. Here we are making use of the condition that mod of f s is less than k times b to the power minus k. So, k times b to the power minus k plus 1 because of this b, and then we have e to the power a x over 2 pi pi by 2 to 3 pi by 2 e to the power b x cos theta d theta. And let us now put this phi equal to theta minus pi by 2, then the previous integral is replaced by integral 0 to pi e to the power minus b x sin phi d phi, and will be multiplied by k b to the power minus k plus 1 e to the power a x over 2 pi. And here now we make use of a property of the definite integral, because sin pi minus phi is sin phi. So, we can write it as 2 times 0 to pi by 2 e to the power minus b x sin phi d phi. And now let us make use of an inequality which is well known. We know that when 0 is less than phi less than pi by 2, sin phi over phi is greater than 2 over pi, and so let us make use of that here. Then this will be further less than k times b to the power minus k plus 1 into e to the power a x over pi integral over 0 to pi by 2 e to the power minus 2 b x phi over pi d phi. And when you evaluate this integral and substitute the limits, it comes out to be equal to k times b to the power minus k e to the power a x over 2 x into 1 minus e to the power minus x b. For x greater than 0, it clearly goes to 0 as b goes to infinity, because e to the power minus x b as b goes to infinity goes to 0, and b to the power minus k goes to 0 as b goes to infinity. And thus, f x is equal to limit of 1 over 2 pi I integral over c f s e to the power x s d s as b goes to infinity. And from a residue theorem in complex analysis, it follows that the value of this integral as b goes to infinity is sum of residues of e to the power x s into f s at the singularities which lie at the singularities of e to the power x s f s which lie in the s plane. And we have taken the line a b in such a way that all the singularities of e to the power x s f s lie to the left of it and are inside the contour. Let us find the inverse Laplace transform of this function of s, 2 over s minus 1 whole square into s square plus 1. Now, we can see that for large values of modulus of s, this f s is asymptotic to 2 times s to the power minus 4. So, and the poles of e to the power x s into f s, poles means the singularities of this function f s occur at s equal to 1 and s equal to plus minus I. At s equal to 1, we have a pole of order 2, and at s equal to plus minus I, we have pole of order 1. These concepts follow from the complex analysis. So, therefore, the residue at this double pole at s equal to 1 will be given by limit s tends to 1 d over ds of s minus 1 whole square into e to the power x s over f s, which after differentiating this we can see that the differentiation comes out to be this. Now, let us take the limit of this as s tends to 1. So, as s tends to 1, the limit of this is minus e to the power x plus x e to the power x. Now, let us find the residue at the simple pole s equal to I. It is again by a formula from complex analysis, it is limit s tends to I 2 times s minus I into e to the power x s over s minus 1 whole square into s square plus 1, which will be equal to 2 times e to the power I x over minus 2 I into 2 I. If you let your s go to I, the denominator becomes minus 2 I into 2 I, which is after simplification half of e to the power I x. Now, at s equal to minus I, we again have a simple pole. So, replacing I by minus I here, we get the residue at the other pole, that is at s equal to minus I. It comes out half of e to the power minus I x. So, now f x is sum of residues of e to the power x s into f s. So, we have the f x equal to minus e to the power x plus x e to the power x plus half of e to the power I x plus e to the power minus I x, and we know that half of e to the power I x plus e to the power minus I x is cos x. So, the inversion formula for the Laplace transform gives us f x equal to e to the power x into x minus 1 plus cos x. One can verify that f x is having this value directly by breaking f s, the Laplace transform of f x, the given function f s, into its partial fractions, and then using the known results, that is the Laplace transforms of elementary functions which we earlier done. So, from there also one can see that f x comes out to be this. So, now let us apply the Laplace inversion formula to heat conduction equation. Let us now determine the flow of heat in a semi infinite var x greater than 0, when initially the var, we are writing it as a solid here, but we are considering a semi infinite var here. So, when initially the var is at 0 temperature, and at t equal to 0, the boundary x equal to 0 is raised to a temperature u naught and maintained at u naught. So, here we are given the initial condition that at t equal to 0, the temperature of the var is 0, and we are given one boundary condition that at x equal to 0, for all the time t, u x t is equal to u naught. And we know that the heat conduction equation in one dimension is delta u over delta t equal to c square delta square u over delta x square, where x is greater than 0 and t is greater than 0. We are given the boundary condition and initial conditions as follows. The initial condition is at t equal to 0, u is equal to 0. U denotes the temperature, it is a function of two variables x and t, and we are given the boundary condition that at x equal to 0, u is equal to u naught for all the time t. Now, let us multiply the partial differential equation by e to the power minus s t and integrate with respect to t from 0 to infinity, and use the given initial condition, that is at t equal to 0, u is equal to 0. Now, when you take the Laplace transform of the left hand side, c square is a constant, so it will remain as it is, delta square over delta x square, x is independent of t. So, we will get, after multiplying by e to the power minus s t and taking the integral from with respect to t from 0 to infinity, we will get delta square over delta x square of u bar, and then the right hand side will be Laplace transform of delta u over delta t. So, that is s u bar x s, t is replaced by s because we are integrating with respect to t, and then minus u x 0. So, this follows from the Laplace transform for derivatives which we have earlier done. So, s u bar x s minus u x 0, and u x 0 is given to be 0, at t equal to 0, u is 0. So, right hand side becomes s u bar x s. The second condition is that at x equal to 0, u is equal to u naught. So, when you take the Laplace transform of that, that is you multiply by e to the power minus s t and integrate with respect to t over 0 to infinity, what you get is u bar equal to u naught by s, when x is equal to 0. And now, the general solution of c square delta u square u bar over delta x square equal to s u bar, this u bar is u bar x s, is u bar equal to a into e to the power x root s by c plus b times e to the power minus x root s by c, where a and b are functions of s. Now, we have to find a solution which remains finite as x tends to infinity, and if that is the case, then we must have a equal to 0, otherwise e to the power x root s will tend to infinity as x goes to infinity. So, in order to find a finite solution or a solution which remains finite as x goes to infinity, we must have a equal to 0. So, u bar reduces to u bar equal to b into e to the power minus x root s by c. Now, let us use the condition that at x equal to 0, u r is equal to u by s, u naught by s, this will give you v equal to u naught by s. And so, u bar will be equal to u naught by s into e to the power minus x root s by c. When we take the inverse Laplace transform of this, then inverse Laplace transform of u bar will be u naught is a constant, so it will remain as it is. Then inverse Laplace transform of e to the power minus x root s by c over s is 1 minus if x over 2 c root t. In view of the result, that is L inverse of e to the power minus c root s over s equal to 1 minus if c over 2 root t. Now, where if denotes the error function defined by if x equal to 2 over root pi integral 0 to x e to the power minus u square du. So, the solution of the given problem is u equal to u naught 1 minus if x over 2 c root t. Let us now consider the case of an infinitely long string which is semi infinitely long string. At the end x equal to 0 of the string is at rest initially, at t equal to 0 it is at rest. The end x equal to 0 is given a transverse displacement f t. We have to find the displacement of any point of the spring at any time t if the displacement by x t is bounded. So, we are giving this thing transverse displacement to this spring to the string at the end x equal to 0, and this is the differential equation which governs the transverse displacement of a string, that is delta square by over delta t square equal to c square delta square by over delta x square, where x is greater than 0, t is greater than 0. We are given that at x equal to 0 the displacement is 0. So, by x 0 is equal to 0 and the string is at rest at t equal to 0. So, delta over delta t by x 0 equal to 0, and we are also given that by x t is bounded and at x equal to 0 by x t is equal to f t. Now, let us take the Laplace transform of the given partial differential equation. We will have this equation. After using the given conditions, it reduces to s square by bar equal to c square delta square by bar over delta x square. By 0 t equal to f t gives you by bar equal to f s at x equal to 0, and by x t is bounded. So, by bar x s is also bounded. This equation gives the solution as by bar x s equal to a e to power x s by c plus b x e to power minus x s by c. Since by bar x s is bounded, a must be 0 and b equal to f s in view of by bar equal to f s at x equal to 0. Hence, by bar is equal to f s into e to the power minus x s over c. Now, let us use the inversion formula for the Laplace transform. We have y equal to 1 over 2 pi I integral over a minus I infinity to a plus I infinity f s e to the power t minus x by c into s ds, which is equal to f of t minus x by c. Now, in our next lecture, we shall be doing the application of Fourier series to the solutions of heat to find the solutions of heat conduction equation and wave equations. That is, we will be applying Fourier series method to the boundary value problems in one dimension case. Thank you.